In this week's lab, the accelerometer that we're going to be using is this LSM6DSO. And this, in the slides, there's a link here to that product page, and in the pre-lab there's actually a direct link to the hookup guide, so you can download the driver library. See, the breakout board that SparkFun makes has a surface mounted accelerometer here, very small MEMS type device, and this guy has, again, 3 axes of acceleration. So it actually, if you look on the device, they show you the Z is out of the board, and then the Y is in this direction. This was positive in this direction. Of course, it measures plus and minus, and then the X is in this direction. All right, so just so you know, when the signals come out, you can get X, Y, Z, and you also get the angular velocities. And let me show you how. I'll show you real quick the software that we're giving you to run the Arduino acquisition, how to tie that with an Arduino DAC driver, and to pull out all 6 of these data from this device. Okay, this is the whole sensor system, right? So the MEMS device is this little box, and this is from their data sheet that you can download from that SparkFun page. You can see it's got the gyros, accelerometer, kind of a block diagram from it. It's actually a temperature sensor on board I've never used before. There's A to D converters that pull in that data, and then there's low pass filters on board. All this stuff is integrated on this little chip. And then the way we communicate with it, right, and you know, we don't, like some of these older accelerometers, we were grabbing analog data, so we need A to D converters. Now, you know, all of this is done through the I2C communications with this device. So that's what this device driver is going to handle for you with Arduino, and you can set up so many different types of parameters. This device actually allows you also, you know, we talked about range of acceleration. You can also tell it what range of acceleration you're trying to detect, so you can set it to the range that you need, and that actually also ends up changing, you know, the bandwidth, you know, what range of frequencies is useful for. So you should look at the data sheet if you ever use this beyond, you know, what we're doing in the lab. We again have a host, which is the Arduino, that you can manage this. You can use multiple ones of these little breakout boards, but you do have to, like, you can use 2 or more of these, but you have to address them differently. It's a little challenging, and we've done it before. Won't get too much into that in this lab. Some of the key specs, again, you can find on the data sheet. You can I think there's a typo here. This is should be a slash here. 2, 4, 8, or 16G range, and the rotational range is here in degrees per second. The sensitivity will depend on the full scale range. So for example, if you put it in 2G mode, and the Arduino code shows you how to do that, how to set it. It tells you what the range, like what the conversion is, the least significant bits, because you'll be reading integers out of that, and then you can convert that into G's. So depending on what range you have, right, you're going to have a different conversion to tell you how many G's you have. And again, that's done in the Arduino. So like for 2 G's, the way you convert that to milli-G's, right, is multiplied by 0.061, whatever integer value you might pull out, right, from the sensor. Okay. The output data range tells you something about the bandwidth as well, and that changes also depending on what range you're using. Okay. Finally, there's some low pass and high pass filters that are in there that we don't use a whole lot in this lab. Okay. It says that there's a shock, like it can handle shock of 20,000 G's, which is pretty high. We haven't tried that, and please don't try that in the lab either. Okay. Let me show you the setup. Again, what I'd like for you to do is walk away from this lab knowing how to hook this sensor up, know how to grab data from it, and be able to reliably measure acceleration. We'll set it up into a simple mass spring damper system configured as a nice beam. And why do we use a beam? Is because it's a reliable vibration. You know, we strap it onto the end of the beam, and That way it's only moving up and down, right, in 1 degree of freedom for the most part. You know, you want it to be strict about it. You know, at the tip of the beam, you do have some slope. So, you know, you could look at the angular velocity at the end and be measuring the angular velocity of this. But we're just going to be looking really at 1 degree of freedom. It's small vibration, right? We sometimes have had another one hooked up here. We're going to do a couple of tests in the lab that the TA will guide you to do to make sure that the sensor's working right and so on. How to hook it up, you know, to the Arduino. We'll walk you through all that so that you'll feel comfortable using this device. Again, this is a dynamic systems and controls lab, so we do a little modeling, and you know, modeling that beam as a simple mass spring damper is one part of what we're going to try to do. We're going to try to figure out what is, you know, confirm the stiffness of this. What is that? What is the mass? We know these here. We can estimate these as you know, from basic formulas. Referring to some of the formulas on the first video that I talked about, there's always a little bit of beam mass on here that we include, and that influences the undamped natural frequency. So you're going to kind of confirm that in some of your measurements. So again, nice simple setup that you'll play with, and if we can model this as a mass spring damper system, that means it's going to follow that response formula that we talked about. Like if we give this, if you very carefully deflect the tip of that beam, right? Just deflect it slightly at the end here with some x naught, right? Release it from rest, so x dot 0 is 0. Then the response is a real simple little formula. There's no step input, so it's really just whatever the initial condition is, that's gone, and it looks just like this here, right? An exponential. I'll give you a little Python code, and I'll show that to you in a second, that will predict that response for you, right? And then what we want to know is, you know, we also want to estimate the damping ratio and the undamped natural frequency of that beam. Also walk away with knowing, you know what is the appropriate, you know, the formula for the natural frequency, undamped natural frequency for when you have a cantilevered beam is you know, whatever the end mass is plus there's a number here, 0.23 times the mass of the beam, and that gives you a better estimate of the undamped natural frequency. I'd like for you to confirm that. This comes from and I give the reference in a previous video. So try to confirm this little formula. Does that give a good prediction? Once you know that, then you know you can say, yeah, I can use these little formulas for whenever I'm trying to estimate the undamped natural frequency of that kind of a configuration. The whole part of this again is for you to make good measurements on purpose, right? Get the right answers and so on. Okay. So in the lab, you're going to study, you know, basically how to be able to capture data, match it to the model, and then use the data to determine parameters, and especially the ones that we can't measure directly. Right. First, let's go to the Arduino. You'll get this code in the lab, and note that you're going to include this SparkFun driver that you'll download on your computer, and you can call this anything. I'm calling it my IMU. It's really not strictly an IMU, it's an accelerometer, but they call it my IMU. And then there's a couple of things. All of this is usually, you know, the same. It's about how our code works, right? And then note that each of these values that we measure, the accelerations in the XYZ, angular velocities XYZ, are all the integers. They're defined as integers. Here's our setup code that sets up a couple of things. First, it sets up the baud rate, but also right here, this line 46, we're setting the acceleration range to 2, which means it sets it to the 2G range, okay? You can change that, as you can see, to 16, 8, or 4, and also the gyro range is 125 degrees per second, okay? So yeah, it's in the setup where you would tell it, this is the range I want to measure. So take a look at that code. And then our code is all the same, except now we're making those 6 measurements. We're going to grab all the data. And remember, the way this code works is I've already uploaded this to my Arduino. It's either sending data via, you know, Python's asking it for the data, and that's the first part of this code here. There's another else if here is if you just want to do a free run, like if you just want to use the serial monitor, okay? So it'll just send this data to the serial monitor so you can sort of test your signals before maybe you'd use Python. So it's going to send them here. That's if you go here and try to run that, you just go to the serial monitor. It's not going to show you anything, right? Actually, this is previously run. It's just, remember, you have to type. I ask it for an F, 50. Tells it do free run at 50 hertz if you like, and it starts sending me data. Right. So this code can be used either with the Python code, or you can use it for free run. Close this guy. You can also run the plotter if you like. And you got to do the same thing down here in the message. You got to tell the Arduino, hey, send me some data. And let's see if we can go a little bit higher rate. Let's try 200. And I've got my the sensor here, and I'm just going to move it here. It's on my desk, holding it in my hand. So oscillate it here, right? So note flipping it around so you can see. Again, you're just testing the signal. So let's say I've got it up and down. So note I've got 1G on the z-axis. I'm going to flip it over, and now it's negative 1G. Okay, that's it's called the 2G test. You're going to do that in the lab, right? You're flipping it from positive G to minus G, and that's one way to check calibration. Let's put it in the Y direction. So now they see the Y, which is the red one, is now 1G. Flip it over 1G, and that's a quick way. Now let's do that for the blue. Quick way to test your calibration. Okay, that's the 2G test. And 2G test, let me just show you a really quick video I have here. I'm going to stop this. All you do for a 2G test, and I've made a video here, you just put it on the table, put it in your hand, but just flip it over really slowly. Just flip it like this. This is the z-axis, and then flip it back. Okay. Again, it's going to read. Make sure your baud rates are the same. I'm going to read it 100 hertz. I'm going to take the data for 10 seconds. And note, I'm asking it to give me all the data. And note the difference now. The time is still a long word, but now H here represents integer values for all the data here. And then it just reads the data as before. Okay, so let's run this guy and let's take some data. I'm going to just, I'm going to do a really quick 2G test while I'm taking data. So first, let's run it. It's sitting on the table. This thing's going to connect. And you'll see that message down there in the open window. There it is, connected. It's going to start. Recording data. I'm going to now do a little 2G, go positive, and negative. Stop. Not moving anymore. And there, took data. Then you go to your read plot Python code, which I also give you, and you'll put in the name of the file here. I just took a new one, so this is an old one. This is kind of what it looks like, just as in the interest of time. If I run this guy, it's going to plot all the data. Note I have the conversion in here, and you'll see what like a 2G test would look like if you there's the gyro data. But there it is. Start off plus 1G, flipped it over, minus 1G, flipped it back, and this is the z-axis. Okay, so you're all ready to go. Now you can go do your experiments as we discussed in the lab.